Well, I've been wanting to do this work for some time, but yeah, I was kind of fortunate that Chen Chang took me on as kind of an overage assistant. Really, she should be giving this talk, but she couldn't be here. But symplectic reduction, let's just do the classical setting of a Lie group acting on a symplectic manifold. And the action is Hamiltonian. I have a model map. So here is what I want to try to more or less explain. The following diagram well, if you have an action, you get an action groupoid with source and target map. It describes the action, but over that groupoid lives a vector bundle, the trivial vector bundle with fiber G star. I'll write the fiber first. And the moment map, of course, gives you a section of that. And you have that bundle just as well here. And let me write it as G cross G star cross M. And that's a vector bundle of this groupoid. It is a vector bundle groupoid. And here too, the moment map gives you a section. And there's a little more. There's a symplectic form here. And also there's a symplectic form here, just a symplectic form on the cotangent bundle. Trivialized cotangent bundle of the group. And the diagram with these two forms represent zero shifted, derived symplectic groupoid. And it is Morita equivalent to the Lagrangian intersection well, there's the cotangent bundle of the group. Which is a groupoid over G star. A groupoid with a symplectic form on the arrow space. So let me record that. And this groupoid, this symplectic object, has two Lagrangians. One is the trivial groupoid with fiber of the group. And the other is, what's the other one? The other one is the action groupoid. you can regard these groupoids as Lagranges in the symplectic groupoid and take a derived intersection, and that's equivalent to this diagram. We label them. So either of these diagrams we will call the derived symplectic quotient. Let me denote it by M mod G. It's a habit people have of putting brackets around something if you regard it as a stacky object of M at the zero level. You can also reduce at orbits other than the zero level, at levels other than zero. That's a slight modification of either diagram. Either in diagram, the first diagram, can do a shifting trick. M with the product in the first diagram, or in the second diagram, replace this diagram, which represents the zero orbit, with the action groupoid of that orbit O. What?
Any restrictions in the neighborhood?
No, none. Absolutely. Oh. So let me write that second diagram a little differently. Groupoids represent stacks. An action groupoid represents the quotient of the manifold by the group action. That's the left leg. And at the bottom we have, so regard this as the action groupoid for the coadjoint action, and this groupoid represents the stack of coadjoint orbits. A point modulo the group that represents the classifying space, viewed as a stack. So what are some features of this derived symplectic quotient? I think we all know that there's two ways in which singularities arise in symplectic reduction. The zero fiber can be singular. And then the action can have fixed points on the zero fiber. That's two kind of opposite way in which singularities arise. But this construction deals with that well, so this is well defined. Even if 0 is not a regular value. B, G does not act freely. On the zero fiber. Or even if G is not compact and does not act properly. So two different features take care of different problems. It's the derived aspect, which is that vector bundle groupoid with the section aspect that takes care of the first problem. So and the groupoid aspect that takes care of the other two. The kind of opposite kinds of problems are taking a fiber categorically is like taking an inverse image, a limit, whereas taking a quotient is like taking a co-limit. So that's one feature. Well, like ordinary groupoids, derived groupoids have orbit spaces. Of course, quotient. By looking at that section and taking its zeros, that's just the zero fiber, and then restricting that action groupoid on the bottom to that zero fiber, and just taking the orbit space. So that's the ordinary Marsden-Weinstein quotient. Viewed either as a topological space or, if you wish, as a diffeological space. You have natural plots on this space in a natural form. And the derived groupoid sees all that information. And so as a topological space or diffeological space. Finally, let me put it here. At each point in that classical quotient, you have three things. There's a natural stabilizer, which is a Lie group, which is in this case just the stabilizer of the group under the action. And then more importantly, a tangent complex, kind of a stand-in for a tangent space. It's a cochain complex, which in the middle has the tangent space to the symplectic manifold. And in and out of that, out of this you have the derivative of the moment map at x going to G star. And into it you have the orbit map. Lie algebra element goes to a tangent vector to the orbit. And then it continues with zeros. And there's degrees here. This lives in degree 0, degree 1, -1. The cotangent complex well, that's just a dual. So dualize each spaces and the maps, and then you swap the grading around. G star star, this gives you G back. Here you get Tx dual, cotangent space, and here you get G star. And these complexes, they're not completely well defined. They're well defined as objects in the derived category. So well defined. And if you replace the groupoid by an equivalent one, the complex may change, but the cohomology groups won't. And the pairing between the two. I think you can see the pairing, it's quite obvious. So let me call it lambda, associated with the symplectic forms, the two forms I wrote there, from one to the other. So what's the pairing? Oh, here it's just the identity map. And here it's just the symplectic form of the tangent space. Now it so happens that this pairing of these complexes is non-degenerate on the nose here. But in general, it will be non-degenerate only after you take cohomology, so which is cohomologically non-degenerate. Yeah, you could say yes, yes. Isomorphism in cohomology, yes. Okay, so why are we doing this? Well, I have my own private reason. Basically an old problem that I worked on, quantization commutative reduction. If both the manifold and the group are compact, then this coarse quotient, you can more or less desingularize it. There's partial desingularization. Which is a symplectic orbifold. This was done by Francis Cohen. So non-singular, up to finite quotient singularities.
Is this the one where it takes like nearby value of value?
That's another way of desingularizing it. Francis Cohen did it a little differently. You start at the deepest stratum, and you start blowing up in normal directions. She did it first for the Kähler case, but then she observed you could do it symplectically just as well by using.
Slightly nearby was that and Edward?
I suppose so. Yeah, and that won't really be a desingularization because then you change the coordinate orbit. Yeah, so then it's a partial desingularization, but also with a change in dimension. There are fibers which are coordinate orbits. But those don't matter for the quantization anyway. What do I call poor man's quantization? Not really what people. So if an equivalent pre-quantum line model, you can define an equivariant index Q of M, which is a representation of the group, a virtual representation, an element of the representation ring, kind of a quantization. That's not a real vector space even, it's not a real representation, it's a virtual representation. It doesn't have a star product or anything of that nature, it doesn't even have an inner product. And that quotient orbifold, that blown up orbifold, also has an index, a non-equivariant index, which is a number. I just call the quantization of my singular quotient the index corresponding to that the desingularization. So you can define that and you can show something. This index is exactly the multiplicity in this virtual representation according to the trivial weight. So I did that a long time ago with Eckhart. But there's a definitional question here. First of all, as Yael pointed out, there are many ways to desingularize. How can you tell a priori whether the quantizations will end up being the same? Or even you could start with a completely different Hamiltonian G-manifold and reduce and end up with what looks like the same singular symplectic quotient. Is it going to have the same quantization? And we couldn't answer that question. And we hope maybe to answer that question using that derived symplectic viewpoint, where you carry along more structure, you remember more structure. Every point has a nice, well, not a tangent space, but a tangent complex. And everything is represented by groupoids. So there's maybe a good index theory and a virtual character you can associate with this. So, question. Show that. Independent of the way you desingularize and of the way you write it as a quotient. Yeah, so a posteriori, you see that here, however you desingularize, it's going to give you the trivial multiplicity. So if you write it, yeah, but what if you wrote that singular symplectic quotient in a completely different way, as a quotient of a different Hamiltonian G-space or a different group? Yeah, then you lose grip. Then you lose your grip on this. So that really is the question.
So I think you're asking about the well-definedness on the left-hand side?
Yes. Yeah, so is it well defined?
Well, the question is, what structure do you need to make sense of it, right?
That's right.
Telling us that, you know, static or derived. So let me.
Sorry, this is kind of stupid. But when you talk about the reduced space, two reduced spaces being the same coming from different actions.
Yes.
What do you mean by the same?
Well, equivalent
But
as
that's part
derived
of the
stacks.
well, that's part of the challenge, right?
Equivalent as derived stacks.
So now comes the question. So for this, let me ask you to make a guess. Suppose that they're equivalent in a weaker sense, you know, and I'm always asking you to try and bat, will or will not their quantizations be the same? Suppose they're equal as stratified spaces or diffeological spaces. Do you have some guess as to whether that might be enough?
My guess is that that's not enough.
Okay.
Yeah, certainly the stratification doesn't carry enough information about the structure local to, orthogonal to the singularities.
And do you have any
The
gut
diffeology.
feeling about diffeology? Like in the context.
Sure. My gut feeling is that no, that's still not enough. You lose your grip on, I mean, it's hard to define in the diffeological world what you mean by tangent spaces, what you mean by non-degeneracy of a form.
No, I'm thinking of just view the reduced space as a subquotient. It has no
Sure, yeah.
But then there's a question of how to define quantization.
Yes.
So it's not just whether or not it's...
You need an operator, some kind of
so you're
elliptic
saying
complex.
It's not just whether the quantization is determined, but how do we even define it?
Yes. More questions?
So what I was asking is, can you define quantization in the diffeological index quantization?
For any weaker space, at least simply connect so technically. There is always quantum bundle.
Yeah, no, he won't.
Quantum bundle.
No,
So
he does not want the pre-quantity, he wants the index theoretic.
Yeah, this is
That's a valid question.
Maar het bundel exist.
Ja.
Maar het bundel exist al.
Yeah, but can you actually push it through the index? Yeah, I don't know.
Okay.
Thank you.
Nothing I've said here may come as a surprise to some of you. There's certainly lots of antecedents to this statement in the literature. Let me just mention a few threads of work on which this builds. I mean, I think it was already known in the 1960s that the one way to desingularize a group action is to regard it as a simplicial object. People like Bott and Schulman did that, Siegel, and so simplicial methods. And the action groupoid is nothing more than the one skeleton of that simplicial resolution. So certainly this work builds on that. The idea to look at these groupoids with symplectic structure not on the base but on the space of arrows. That goes back to Weinstein. Symplectic groupoids. Shipping.
Reyer, I would just suggest maybe not.
Oh, yes, I forgot about that. So I can use the upper half of this board, or should I just not use it? Okay. So, yeah. So in today's language, a symplectic groupoid just means a one-shifted symplectic, underived one-shifted symplectic one groupoid. I won't talk about the higher groupoid aspect much, but it will be just one groupoid, plain groupoids. That is work of Andre Enriquez and Getzler and others. Chen Chung herself. But most of all, the idea of presenting a symplectic quotient this way, I think, goes back to algebraic geometry, recent work in algebraic geometry. we're dealing with, say, a non-singular complex algebraic variety and a reductive group acting on it, preserving a complex symplectic form. And certainly they prove theorems like this. So that's work of people like Pantev. Kalak and Safronov. So in a sense, what we're doing here is transcribing some of this in a language of differential geometry. And one thing we'll also lean on is a paper by Kai Behrendt and some collaborators. And there are people in this room who also work on aspects of this story, but I can't write down all the names, I'm sorry. So what do we do? What's the technical tool? The technical setting in which we develop this. You could call it homotopical algebra. It's kind of a non-abelian homological algebra. The ideal version is model theory, which is due to Quillen. Okay, model categories. It wasn't doing logic. And his student, my retired colleague, Ken Brown, noticed that you could get by, if necessary, with pretty much just 1/2 of the structure that Quillen considered. The category of fibrant object, it's a category. I won't write down the axiomatics, but it has 3 special classes of arrows. One is weak equivalences, which you think of as homotopic equivalences. And another class called vibrations, and which typically in a geometric setting are things like submersions and so on. And path objects. And let's see, my timing is being completely thrown off by having to give this talk on the board. So what time did I start and what time am I supposed to end?
8 minutes, technically, we can push it slightly.
Oh God. Yeah. I have to completely change this. In the remaining few minutes, let me just try to make sense of a few aspects of the theorem which I stated. Let me skip this. So let me describe what Beer and Liao and Xu did. So, because we simply combine their language with the language of groupoids. That's the gist of it. So a derived manifold, that's simply a differential graded manifold of positive amplitude. A DG manifold of positive amplitude. So what that means, it's a triple, it's a manifold with some extra structure. Bundle, finally graded bundle, and some operations on them. So M is a manifold. And E is a graded vector bundle over M and some operations. Graded symmetric multilinear operations. So a sequence of operations, the J's operations goes from, it takes J arguments, and then raises the total degree by 1. And this is for J greater than or equal to 0. If J is 0, then you have no factors here, then you just have this trivial one-dimensional line bundle. So a map from the trivial one-dimensional bundle into E1. This means a section of E1. So lambda naught is just a section, like that moment map in the symplectic reduction setting we had. So N derived manifold is a classical locus the zeros of that section. And at each point in the classical locus, there's a tangent complex. The trivial line bundle with fiber R. Is that okay? Sure, sure. Yes, fine. Yeah. So this tangent space at the base manifold, and then it goes into the fiber of that first structure bundle at X. What do you do? Well, you always, you basically take that section, and you can always differentiate, say covariantly, but at the zero section, at the vanishing point of the section, that doesn't depend on the connection. So let me just call that the derivative of that section. This point where it vanishes. And then it's a complex that continues. It's a complex in real vector spaces. And this uses the other structure maps. Mm-hmm. It's made up out of these structure maps. Okay, sorry. And they define a structure of a CFO, a context in which you can do homotopy theory, a context in which you can do pullbacks, you can take fibers, in which you can take, for example, So derived. I'm already out of time, I suppose.
Yeah.
Okay. There's no way I can do justice to my notes.
He's gonna give you a little bit.
You need an extra couple of minutes.
Yeah. Okay. So the final punchline is just to put together the structure of Lie groups together with the structure of derived manifolds. That's really it. Let me just end by saying that I have no time to explain how you manufacture differential forms and how you get that pairing. So. The derived Lie groupoid is just a Lie groupoid object in this category. In the category of derived manifolds. And the one I showed you at the very beginning, the one you get from a Hamiltonian G action, well, there's only one structure bundle. You only have the section. Yeah? And we only have a one groupoid, only an action groupoid. We don't even need higher groupoids, although you need them in other contexts. Okay, well, sorry for the technical snafu, but yeah, I have to skip most of my notes. Sorry. Okay.